All right, we're going to graph the sine and the cosine function in this section. All right, I'm going to grab a laser pointer to help me out here a little bit. Now, the graphs of the sine and cosine, they actually look like waves. And in general, we call those types of waves, or in this particular type of wave, a sinusoidal relationship. Okay, notice the root word for sine, and sine is a root word. All right, so the way we're going to do this is we're going to get a graph here, and then we're going to get a table of values. All right, and we're just going to plug values in for theta, evaluate their sine, and graph it. So, for example, if theta is 0, the sine of theta is 0, sine is 0, 0, and we're just going to plot that on the graph right there. All right, and we're going to go through a complete period of the wave, or a complete wave. So pi over 4, the value for sine of pi over 4 is root 2 over 2, and decimal equivalent is 0.707, so it's going to be roughly right around there. When theta is pi over 2, the sine of pi over 2 is 1, so we're going to plot that. Continuing, 3 pi over 4, the sine of 3 pi over 4 is once again root 2 over 2. The sine of pi is 0. I'll plot that. The sine of pi, 5 pi over 4 is negative root 2 over 2, negative 0.707. The sine of 3 pi over 2 is negative 1. The sine of 7 pi over 4 is negative root 2 over 2 again. And finally, the sine of 2 pi is 0. And so we have now one complete wave. And I'm going to connect these. I'm not going to connect the dots. I'm going to draw a smooth curve through these points, and it's going to look something like that. And this is the parent function for a sine wave. All right, let's plot the cosine function now. All right, so if theta is 0, the cosine of 0 is 1. So we can plot that right there. The cosine, if theta is pi over 4, the cosine of pi over 4 is root 2 over 2, which is 0.707, which is right around there. If theta is pi over 2, the cosine of pi over 2 is 0. If theta is 3 pi over 4, the cosine is negative root 2 over 2, negative 0.707, right around here. If theta is pi, the cosine is negative 1. If theta is 5 pi over 4, the cosine is negative root 2 over 2. If theta is 3/2 pi, the cosine is 0. If theta is 7 pi over 4, the cosine is root 2 over 2. And then finally, if theta is 2 pi, the cosine is 1, which is right there. And then we can draw a smooth curve once again, and we'll get something like this. And this is the parent function for the cosine. Okay, I want to introduce some vocabulary now. And this is just a general sinusoidal wave that I'm going to use to do it. And the first one I want to introduce is something called the equilibrium position. Equilibrium position. And this is like the rest position of the particles of a medium. Picture it like a very still lake. The surface is very still before like a water wave passes through it. It's the rest position of the particles before a wave passes through that position. We call that the equilibrium position. Okay? All right, another term I want to introduce is amplitude. Amplitude is the maximum displacement from the equilibrium position. Okay, so it's the maximum displacement of the particles as a wave passes through it. And we denote this by A. So this is the distance from the equilibrium position up to the top of the wave, or the bottom of the wave. Okay, and that's called equilibrium. I'm sorry, that's called amplitude. Next one I want to introduce is period. Period is defined as the change in theta values required for the function to complete one complete cycle. Okay, so as we increase in theta here, the wave goes through one complete cycle from 0 to here. Okay, we denote that by T, capital T, right? And that's the theta required for one complete cycle of the wave. All right, and we denote that by cap T. All right, one more term I want to introduce, and that's frequency. And frequency, I'm going to define that as the reciprocal of the period, which I realize that doesn't mean a whole lot right now, but as we apply it to actual waves, waves in water, sound waves, things like that, that will become more visual, or we'll get some meaning out of it. Right now, we're just going to call it the reciprocal of the period. And we're going to denote it by small f. Okay, and actually, honestly, we're not going to do a whole lot with that other than just identify it at this point in time. Okay, now I want to introduce the general equation of a sine wave, of a wave. Now, the simplest one will just be f of theta equals sine theta. But in general, we can insert a little more complicated stuff. We're going to call it this: f of theta equals a sine of b times quantity theta plus c plus d. Now, what do these letters mean? What do they represent? Well, a represents the amplitude. B represents the horizontal shrink or stretch. And this is kind of recalling, we did this with transformations, which is kind of the same thing as what we're going to do here. C is the horizontal shift, left or right, and D is the vertical shift, up or down. Okay, now as an example, let's apply it to this function, f of theta equals twice the sine of theta. All right, so I'm going to get a graph here, and I'm actually going to get a table of values, theta, sine theta, and then the function itself, 2 sine theta. All right, so plugging in a value for theta, 0. The sine of 0 is 0, but we're not really interested in that. We're interested in actually 2 sine of theta, but is sine of theta is 0, twice that is also 0. So at 0, the value of the function is 0. We can plot it right there. Okay, now let's go to pi over 2. Now the sine of pi over 2 is 1, but we don't really care about that so much. We want twice that, so we're going to have a value of 2. So to scale my axes so that everything fits, I want to put 2 up here. So at the value of pi over 2, the function has a value of 2. So that means the amplitude of the wave is 2. But that makes sense because note that a is the reciprocal, the number in front of the sine function, and that represents amplitude. So the amplitude is equal to 2. All right, let's keep going. If theta is pi, the sine of pi is 0, and twice that is also 0. So at pi, the value of the function is 0. At 3/4 pi, the value of the sine function is -1. And the value of our function, the one we're graphing, is -2, which we're going to plot there. And then finally, going through one complete period, if theta is 2 pi, the sine is 0, and twice that is also 0. So we're just going to plot it there. And then we're going to draw a nice smooth curve between these, and we get something like that. And that's our sketch for this example. All right, let's do this function. The sine of 2 theta now. All right, so again, inserting values. Let's call theta 0. The sine of that is 0, but we're not really interested in that. We're interested in the sine of 2 theta. But if theta is 0, twice theta is also 0, and so the sine is just 0, which we can plot there. All right, at pi over 4. Now the sine of pi over 4 is root 2 over 2, but we're not really interested in that. Instead, we're interested in the sine of 2 theta, so we're really interested in the sine of pi over 2. Pi over 4 times 2 is pi over 2, and the sine of pi over 2 is 1. All right, so that at theta being pi over 4, the value of the function is 1. At pi over 2, the sine of pi over 2 is 1, but again, we're not really interested in that. We're interested in the sine of twice theta, so we're really interested in the sine of theta. Pi over 2 times 2 is pi, and then the sine of pi is 0. So at pi over 2, the function has a value of 0. At 3 pi over 4, the sine of that is this, but 2 theta, if 3 pi over 4 times 2 is 3 pi over 2, and the sine of that is -1. which we can plot here. And then finally, if theta has a value of pi, the sine of that is 0. Don't really care about that, but the sine of 2 pi is also 0. So we can apply this. Okay, and then we can connect them to form one smooth curve. Now notice our parent function had a period of 2 pi, but this one has a period of pi. So we have shrunk this thing down by a factor of 2. This is a horizontal shrink of 2 because it changed the period from 2 pi to pi. Okay, and as you recall, that the coefficient from transformations was a horizontal shrink. Okay, so anyway, it's kind of the same thing. But now what that allows us to do is get an equation for the period in terms of b, in terms of this value right here. The period is going to be 2 pi over b. And we're going to use that as we go here. Okay. Okay, let's do this example. Now we want the graph of sine of theta plus 2. All right. So getting some values once again at 0. The sine of 0 is 0, and 0 plus 2 is 2. So I'm going to kind of look ahead, and I'm going to scale it like that. And I'm going to plot right there. At pi over 2, the sine of pi over 2 is 1, and 1 plus 2 is 3. Goes right there. When theta is equal to pi, the sine is 0. Add that to 2 to get 2. At 3 pi over 2, the sine is negative 1. Add that to 2 to get positive 1. And then finally, at 2 pi, the sine is 0. Add that to 2 to get 2. And then we've gone through one complete period, so draw a smooth curve. And notice that all this has really done is to shift this sine wave up 1. It has an amplitude of 1, and we've just taken that thing and just shifted it up 2. It's a vertical shift up 2. But as you recall, d was our vertical shift. D has a value of positive 2, so that makes sense. Okay, one more example. We're going to graph this function, sine of quantity theta plus pi over 4. All right, so let's get ourselves a table of values. And looking ahead, I'm just going to scale it like this. All right. Now, at 0, the sine of 0 is 0, but we're not really interested in that. We're interested in the sine of theta plus pi over 4. 0 plus pi over 4 is the sine of pi over 4. And the sine of pi over 4 is root 2 over 2. So at theta is equal to 0, the value of the function is right about there, 0.707. And when theta is equal to pi over 4, the sine is this, but again, we don't really care about that. We want theta plus pi over 4. Pi over 4 plus pi over 4 is pi over 2. And the sine of that is 1. So when theta is equal to pi over 4, the function has a value of 1. If theta is pi over 2, all right, we don't really care about that. But theta pi over 2 plus pi over 4 is 3 pi over 4. And the sine of that is root 2 over 2. So at theta being pi over 2, the value of the function is right here. All right, let's continue. At 3 pi over 4, the sine of 3 pi over 4 plus pi over 4, 3 pi over 4 plus pi over 4 is 4 pi over 4, or just pi. And the sine of pi is 0. So at 3 pi over 4, the value of the function is 0. At pi, okay, we don't really care about that. Pi plus pi over 4 is 5 pi over 4. And the sine of 5 pi over 4 is negative root 2 over 2. So at theta equaling pi, the value of the function is down here. Okay, I'm going to start to ignore the middle here. 5 pi over 4 plus pi over 4 is 6 pi over 4, or 3 pi over 2. And the sine of that is negative 1. for 3 pi over 2, add that to pi over 4, okay? And we get, what, 7 pi over 4? And the sine of that is negative root 2 over 2. At 7 pi over 4, 7 pi over 4 plus pi over 4 is 8 pi over 4, or 2 pi, and the sine of 2 pi is 0. And then just completing one period of the wave, if I go from to 2 pi, then this becomes 2 pi plus pi over 4, which is actually 9 pi over 4. That has the same sign as just pi over 4 of root 2 over 2. And we get to here. And then we can sketch in one complete, draw the curve. We get something like this. Now, notice what went on here. The parent function had its maximum at pi over 2. We have just taken that maximum and shifted it to the left by pi over 4. Okay. This 0 right here used to be at pi. It is now at 3 pi over 4. So we shifted it to the left by pi over 4. So the whole wave, the whole sine wave has been shifted to the left by pi over 4. Okay, so it's been shifted horizontally by pi over 4 to the left. All right, and that's represented, C, remember, was our horizontal shift, and a horizontal shift of pi over 4. Okay, all right. Now, I'm going to get away from calling it a horizontal shift because in general, it's called a phase shift. So this wave has been phase shifted by pi over 4 to the left. Okay. All right, now let's do this example. And we're going to identify some things. We're going to end up graphing this. All right, so first of all, I just want to get an idea of the parent function. This is a sine function, so just for a visual, this is going to be the parent function for the sine with the values, general equation down there. And I want to kind of identify the letters in the function with the letters in the general equation. So that's going to be my A, and that's going to be a B. All right, and that actually identifies if A is 3. Remember, A is the amplitude. So this gives us an amplitude of 3. All right. Okay, and I'm just going to place that in our thing down there. And now B, remember, B is related to the period by this expression. The period is equal to 2 pi over B. And since B is equal to 2, that gives us a period of pi. All right. And if the period of the parent function is 2 pi, and the period of this function is pi, what that means is this function is shrunk down horizontally by a factor of 2. This is a horizontal shrink of 2. Okay. All right. Next, just to fill in this table, we can do the frequency. The frequency is defined to be the reciprocal of the period, and if the period is pi, the reciprocal of that is simply 1 over pi. And we're actually just going to leave it like that, just 1 over pi. All right. Okay, now let's graph this thing. Now, the 0 for the sine function, the origin, it's the at theta equals 0, the value of the function is 0. That's going to be the case here as well. So we can just plot that right there. And now, a horizontal shrink of 2 means that these zeros, the ones at pi and 2 pi, are shrunk down horizontally by a factor of 2. So the 0 that was at pi is now going to be at pi over 2, and the 0 at 2 pi will now be at pi. It's shrunk by a factor of 2. Oh, sorry about that. I forgot my order. Amplitude is 3, so I'm going to scale my axes like this. Okay. All right. Yeah, as I mentioned, the 0 is going to be shrunk down, and they're going to be here and here. Okay. The maximum of the parent function was at pi over 2. It is now shrunk down by half, and now it's going to be at pi over 4. And it will have an amplitude of 3, so it's going to be there. And this maximum will also be shrunk down to 3 pi over 4, right there. Okay? And so now we can sketch, we have one complete period, which we can sketch in. And then just for the sake of completeness, we will kind of sketch in the rest of them. And that is our graph. All right, let's do this. Let's do this function now. Okay. Now let's identify some things. So now this parent function is going to be the cosine function. So I'm going to put the parent function there and our general relationship, and just identify some things. Once again, this is going to be the amplitude, okay, and this is going to be our B, our value for the B. And A now is -2. The amplitude is -2, okay, and which I'm just going to put in our blank there. Now the period, which is 2 pi over B, B is 1/2, and 2 pi over B, 2 pi over 1/2, that is 4 pi. Okay, so 4 pi. And this B is a horizontal shrink of 1/2, which corresponds to a horizontal stretch of 2. So this function is going to get stretched out by a factor of 2. All right? Okay. Now, let's take care of the frequency. The frequency is 1 over the period. The period is 4 pi. The frequency is just going to be 1 over 4 pi. All right? Okay, so we get a value for that. All right, now now we're going to plot this thing. Now the maximum, or the value at theta is equal to 0 for the parent function was +1. Okay, now this one has an amplitude of -2, so the negative sign means the whole thing is going to be flipped, and it will be doubled as well. So -2. So that means I'm going to scale it like this, just so everything fits. And then this maximum here is actually going to be at -2. All right. Okay. Now, this value for 0, the parent function has a value of 0 at pi over 2. But remember, we're stretching this thing by 2. So this 0 will now be stretched out and will be located at pi. And this maximum here, which was located at pi, will now be located at 2 pi. But an amplitude of -2 means it's going to go from down here to up here. And that results in the maximum being here and correspondingly over here. All right, and then the zeros will be, as I mentioned, the zero is going to get stretched out to here. Okay, and then I'm going into the negative just so that it fills out the graph, and so it'll be stretched out to here. Okay, and then the function will be like that, and that shows one complete period. Okay, going from the top of the wave to the next top of the wave, and notice that the period of the original function was 2 pi, but the period of this function is 4 pi. It goes from -2 pi to +2 pi. So the period is actually 4 pi. All right. Okay. Another example. Let's do this one. The sine of 2 times that plus 1. All right. So the parent function, once again, will be sine theta. All right. And now let's identify some things. So I'm going to just put some letters in there. There's an A, there's a B, there's a D. All right. I notice that the amplitude is 2. Okay. And so I'm going to put it in there, right there. Now let's deal with the period. The period is 2 pi over B. B, once again, is 1/2. And once again, that equals 4 pi. So period is 4 pi. And once again, as in the previous example, this actually results in a horizontal stretch of 2. Okay, so once again, we're going to stretch this thing out by a factor of 2. Okay? And then next, we notice, oh yeah, let's deal with the frequency. Okay, so frequency is 1 over the period. Period is 4 pi, so the frequency is going to be 1 over 4 pi. We can just write it in there. We're not really going to do anything with that. We're just going to identify it. Okay? And then finally, notice that D is equal to 1, +1. D represented a vertical shift, so we get a vertical shift of 1. All right? Okay, now let's scale these axes. Looking ahead, if you kind of work this out, it's going to end up, we're going to need to scale this 4 and -4. Okay, and now let's go to the 0. Now the 0 is going to be at a value of 0.
okay? But this is going to be shifted up by 1 because of the vertical shift, so we're going to get a point right there, okay? And our other 0 over here, okay, or 0 over here actually, because this 0 is stretched by 2, it will also be transformed up 1. And that's where we get this. And then at pi, the maximum was at pi over 2, but this okay, next thing to do, we want to write a sine function with these properties. Okay, amplitude 5, period 4 pi, vertical shift down 4, and horizontal shift to the left. Okay, so we're going to start with our general function. And now let's identify some quantities. If amplitude is 5, that's going to be A. All right, let's see now. The period, all right, can be found from 2 pi over B. And the period is 4 pi, so that means that B is 1/2. All right. Let's see what's next. Let's go for D, vertical shift of down 4, so D is -4, and then C is pi over 3. A horizontal shift to the left is a positive pi over 3 for C. All right, and then we can just insert the values. All right, and there's our answer. Okay, let's do this one. With these properties, once again, we have our general function, and let's identify some quantities again. A is 3. All right, I can use the 2 pi over 3 period to find the B, and it can be seen by inspection really that B is equal to 3. And then there is no C. C is 0, and the vertical shift is up 1. All right, so that inserting our quantities once again leads us to this answer. All right. Okay, now we can get a little bit more interesting. Now we have this graph, and we want to get this. We want to get the equation from this graph. Okay. So once again, we're going to start with our general properties, and let's start identifying some quantities in no particular order. But the first thing I did was I noticed that the difference between the top of the wave and the bottom of the wave is 6, and I know that the amplitude is twice that. The amplitude is going to be half of this, so that gives us that A is equal to 3. All right, and I noticed that the difference between the top and the bottom halfway between is right here, and that's the equilibrium position. Okay. And so that means that this whole graph has been shifted down 1. Okay, and that's so D will be -1. All right. Okay, next thing I notice is that the difference between the top of the wave from here to here will be the period, and the period is equal to pi. All right, it goes from 0 to pi. So I can set that equal to 2 pi over B. And that gives us a value for B of 2. Okay. And then finally, I noticed that they want a sine function. Well, remember that the first maximum for a sine function was at pi over 2. So this whole function has been shifted to the left by a value of pi over 2. And that will be c. All right, so that gives us a c value of pi over 2. So from this graph, we can glean all that information. And once we have that, we can just insert it into our equation. A is 3, B is 2, C is pi over 2, and D is negative 1. And that gives us an answer of this. Okay. All right. Now you're in a position to try the practice problems.